This is a solar farm. A solar farm is made up of multiple solar panels arranged together in a grid. But what is solar panel and how does it work? In layman's term, a solar panel is a device that turns sunlight into electricity. But how does it do that? Inside a solar panel, there is a magic material called silicons, and when sunlight hits it, it makes electricity thanks to a process called the photovoltaic effect. But there are a few problems with using silicon as a semiconductor in solar panels. It is expensive to process it, and it is also energy extensive. So, we have come up with an alternative solution that could be affordable as well as compatible. Meet mercury diselenide. The researchers used two liquids, one with mercury and one with selenium. They then added a helper chemical called triethanolamine, which is TEA, to help the elements mix and react properly. Then, they use electricity to help these elements form a thin layer on a surface. This process is called electrodeposition. It's like using electricity to paint a material onto a surface. They changed the amount of voltage to see what gave the best results. So what did they check? They want to check how thick the films were. They want to check whether the materials form correctly using a tool called XRD. It's kind of like microscope for crystals. They also want to check what the surface looked like with a very powerful microscopes like SEM. We can see that from this graph, the thickness of the thin film increases with increasing potential voltage. Analyzing this graph, we can see that the peak for stainless steel substrate decrease with increasing potential voltage. This also shows that the peaks belonging to mercury diselenide increases as the potential voltage increases. However, for the peak at 2 theta, when the potential voltage reached negative 1.8 volt, the intensity of the peak decreased due to the peel-off of the mercury diselenide thin film. This is the surface morphology of mercury diselenide. Thin films observed under the scanning electron microscope at different deposition voltages. At negative 1.2 volts, the image shows a smooth surface, indicating insufficient ion deposition due to low potential. When the voltage increases to negative 1.4 volts, the surface becomes granular with irregularly shaped grains, suggesting better but uneven deposition. At negative 1.5 volts, cracks begin to form, likely caused by stress from higher potential. Finally, at negative 1.6 volts, all ions are deposited, but the surface shows signs of peeling, indicating over-deposition and poor adhesion. These SEM images clearly show how the applied voltage affects the surface quality of the thin films. So, the conclusion is, mercury diselenide thin films were successfully deposited on stainless steel substrate at negative 1.5 volt. The stoichiometric mercury diselenide films were obtained by electrodeposition technique. XRD peaks revealed the presence of mercury diselenides within the thin films, and SEM results showed the growth of film was uniform and well distributed and adhered over the stainless steel substrate.